Good afternoon, Michael. How are you?
Good, Matt. How are you doing?
Fine. Look, you've written exponential function, and I'm really curious because exponentials usually are defined using limits, and we're not using limits, so take me through it.
That's right. Our philosophy in these talks is let's not use limits, okay? Let's use geometry. So the amazing thing about the exponential function is we can use the hyperbola again to define the exponential function, except a different hyperbola.
And which one is that?
This is the rectangular one, the one that we usually see with the reciprocal. So if I put my axis here, I'm going to use a U and a V here for my axes, just so I don't get confused with the X that we use. And the hyperbola looks like this, where V is the reciprocal of U.
So whatever we do in U, we get V just by reciprocalizing it.
That's right. So if we had U equal to 2, V would be equal to?
Half.
That's right. Okay. So here, when U is big, V is small.
But now, how do we use this?
So like we did with the trig functions and the hyperbolic functions, we're going to use areas. And I'm going to start at a very special place where U is equal to 1. And I say, Matt, if you give me a number like 3, for instance, I'm going to go along this line, until I get to a special point where the area under this curve is 3. And that point, I'll call this point the exponential of 3.
So 3 is the area then.
3 is the area. And you can see if I took a bigger number like 5, would I go this way or would I go that way?
I'd go that way.
That way, right. And if I had a smaller number like a half, I would go
that way. And if you put 0 here, then U goes to 1 because at 1 the area is 0.
That's right. So we found this interesting thing about this exponential function, that the exponential of 0 is equal to 1.
So the U-axis is the exponential of whatever the area is as you've drawn it.
That's right. So let's, instead of having this number 3 here, let's put another number, let's say x0, okay? So you give me a number like 3 or 5 or 7, we'll call it x0. I move this line, this vertical line, until I get an area of x0, and that point I define as the exponential of x0.
I'm really curious to see how we're going to get to our good old e to the x function.
We will get to e to the x. It'll take a little bit of work, but the interesting thing is we've just got a very simple function. There's no limits. Nice little hyperbola. We've defined the function. And now I'll show you how to compute the derivative. Would you like to see that?
Yeah, let's do it.
Okay, so you remember with derivatives, we always take our x0 and then we move a little bit to the right or the left of that.
We find the difference in the areas, basically.
That's right. So let's move a little bit further, and I'm going to add a little bit of extra area here. I'll call it x.
So we have a total area now of x naught plus x.
That's right. So this point comes from that area x naught plus x. So this is called exponential of x naught plus x. And keep in mind, x we should think of as being a small number.
Okay, I'm good with that. That's great.
Okay. Now this thing was a hyperbola. So the x-axis we saw was x of x0.
And now
What's the
1
y-axis?
over that.
Exactly, because it's the hyperbola.
It's this one, yeah.
So that tells me the height here, from this point to this point, is how high?
Well, it's the height of v.
So 1 over x
0.
Which is our height.
Well, that's the starting height. It's going to be a little less over
We're
here.
not going to worry about that. We're approximating, remember?
Right.
And remember, x is small, so these things are really close. So,
Okay.
So for our approximation, let's call
That's
it 1
good.
over x plus 0.
Okay.
Now, this looks like a rectangle. What's the area of a rectangle?
Height times base.
So here's the height, 1 over exponential of x0. And
The
it's
base,
multiplied by the base.
which is the difference of those.
That's right. So we take the bigger one, exponential x0 plus x minus exponential of x0. And that equals an area.
Yep.
It's the area of this little rectangle. And do we have a name for it?
X.
That's x. So if I multiply this out the other way, I'm going to move this to the other side. So exponential of x0 plus x minus exponential of x0. This is exponential of x0. I'll put that in brackets, times x. Does that look familiar?
Yeah, it certainly does. This is like the function x naught plus x minus f of x naught, which is a linear approximation in x. So I guess that's the slope.
Yeah, and I really should do
Or the
approximations, and that's our slope.
Yeah,
So that tells me what the derivative is.
yeah, ex of x0.
So here we go. Derivative of exponential at x0 is the same thing, exponential at x0, which is pretty amazing when you think about it. So
Well,
you got
I
a
was just
function.
going to ask you a question because where this whole thing depends on how you defined it, but you're just calling it that, right? But the point is it could be called something else, like popsicle or
I
something.
could have called it popsicle of x0. I could have called it big F of x0. I could have called it big H of x0.
So
we
it's-
call it the exponential function.
Right, and so it's not necessarily like we're using anything about the number e or e to the x. This is just a name.
That's right. It's just the name of this very special function. We're going to have a separate video just to talk about how that's connected with the process of exponentiation.
Oh, I'm really curious about that.
We'll see that next time.
Great, wonderful.